Okay, good morning. In the last class, we have discussed about the IR spectral features of atoms, sp3 hybridized oxygen and nitrogen in functional groups such as OH, NS2, respectively. And then we have concluded with looking at the shapes of bands that comes above 3000 centimeter inverse in an IR spectrum. And today we are going to start discussing about the features of the vibrations of carbonyl functional groups. And carbonyl functional group is, as you know, nothing but C double bond O group. And there are a lot of compounds that contain these carbonyl functional groups. To name, anhydrides, acid chlorides, esters, aldehydes, ketones, carboxylic acids, and amides. And this table gives the symmetric stretching vibrational frequency of carbonyl functional group in these compounds in the order of decreasing their vibrational frequencies. Okay, and for acid anhydride, there are two types of bands. There is a set of two bands, pair of bands, and the first band comes at a higher frequency around 1810 centimeter inverse, and the second band comes at frequency of around 1760 centimeter inverse. And whereas for acid chloride, the carbonyl stretching vibration appears to be at around 1800 centimeter inverse, and in ester, the carbonyl vibrational frequency is at 1735 centimeter inverse. And for the most famous carbonyl compounds, aldehydes and ketones, for aldehyde, the vibrational frequency is at 1725 centimeter inverse, whereas for ketone, it comes at around 1715 centimeter inverse. And for carboxylic acids, the vibrational frequency is at 1710 centimeter inverse, and for amides, it usually appears at around 1690 centimeter inverse. And keep in mind that these values should be taken as base values, because these values can be changed upon by the influence of other factors such as resonance, inductive effects, etc. Okay, and we are going to see how these vibrational frequencies can be changed upon when subjected to features such as resonance, inductive effects, etc. Okay, and this slide gives the spectral the chemical formula or chemical structure of some carbonyl functional groups, which contains different substituents on the or functional groups on the carbonyl carbon, such as alkyl functional groups NS2, then sp3 hybridized oxygen such as the one in a ester setup, and then an acid chloride. Okay, and as far as the alkyl substituted carbonyl group or carbonyl compound is concerned, the alkyl group, as you know, is an inductive electron donor, which can donate the electron density towards the carbonyl carbon, this through a plus I effect mechanism, and that can influence the electron density around the carbonyl carbon, because as you can see, when the electron density is being pulled more towards carbonyl carbon, that can make the carbon oxygen sigma bond more stronger, whereas in the case of nitrogen, in here the nitrogen is able to donate its electron density towards the carbonyl carbon, that makes the bond order around the carbon oxygen sigma bond stronger, whereas the nitrogen is an inductive electron withdrawer that can pull the electron density away from the carbonyl carbon. So there are two mutually competitive processes. One is the donation of the electron density towards the carbonyl carbon by the nitrogen, whereas the other effect is the withdrawal of the sigma bond electron density towards nitrogen through minus I effect. Okay, and the same thing you should be able to see in the case of oxygen, where the oxygen can donate the electron density towards the carbonyl carbon, whereas and the oxygen can withdraw the electron density from the carbonyl carbon through inductive effect. Okay, and as for the acid chloride, the chlorine is also has or is rich in lone pair electrons, and the lone pair electrons can be donated towards the carbonyl carbon, changing the bonding environment around the carbonyl functional group, whereas the chlorine being highly electronegative, it can pull the electron density towards it. Okay, and again altering the carbon bonding environment around the carbonyl functional group in a different way. Okay, so these two mutually competitive mechanisms, and of which these two mutually competitive mechanisms, the dominant mechanism decides the bond strength or the bonding environment around the carbonyl functional group, and it decides the vibrational frequency, stretching frequency of the carbonyl functional group. And we shall be seeing how this mechanism, or which one is going to dominate over which mechanism, and whether it's inductive or resonance contribution. Okay, and how this is going to influence the stretching frequency of the carbonyl functional group. Okay, as for carbonyl compounds containing an oxygen that is being connected to the carbonyl carbon, such as the case of an ester, then you should be able to see that if you see the structure on the right hand side here. Okay, and then you should be able to see that this lone pair electron density on the oxygen can be donated towards this carbonyl carbon, and which results in a shift of the pi electron density on the between the carbon oxygen bond towards the carbonyl oxygen, thus making it negatively charged, and the other oxygen, sp3 oxygen, making almost kind of sp2 oxygen with a positive charge on this one. Okay, and this can result in a kind of resonance structures, okay, which are in which can rapidly interconvert between each other. Okay, and as for inductive mechanism, the oxygen is a highly electronegative atom, and the oxygen should be able to withdraw the sigma bond, or attract the sigma bond electron density towards it. Okay, that would make the carbon delta positive, which would draw the sigma bond electron density towards it. Okay, and as a result, in order to compensate the stiffening of the shortening of the sigma bond electron density, the pi bond becomes more stronger. The pi bond between carbon and oxygen becomes more stronger. Okay, that could result in an increase in the oscillation frequency of the carbonyl functional group. But whereas this mechanism, this results in a weakening of the carbon oxygen pi bond carbon oxygen bond order. Okay, which results in a reduction of the stretching frequency of carbonyl functional group. So one mechanism causes a reduction in the stretching frequency, whereas the other mechanism causes an increase in the stretching frequency. So which one prevails? Okay, that is the question. Okay, and we shall be able to see this or discriminate between these mechanisms, which one favors over the other one. Okay, if we see the electronegative nature of the oxygen, because oxygen is highly negative, so it wouldn't actually, this sp3 oxygen wouldn't actually tolerate to be a positive charge on it. Okay, it doesn't favor the formation of a positive charge. Okay, whereas the negative charge is being favored here, but this oxygen does not actually favor, this sp3 oxygen does not actually favor the formation of a positive charge on it. Okay, but this is a highly favored mechanism compared to this mechanism because of this reason. Okay, so the inductive process or inductive mechanism of pulling the electron density towards the sp3 oxygen dominates over this resonance mechanism. Okay, so there because this one dominates over the other process, what you will actually be seeing is an increase in the pi bond order between the carbon and oxygen in the carbonyl functional group, which results in an increase in the stretching frequency of the carbon oxygen or carbonyl functional group. Okay, so that's what you see. But if you replace the oxygen with a less negative electronegative atom nitrogen, okay, still you would see these two mechanisms: resonance effect, resonance contribution from the sp3 nitrogen, as well as an inductive contribution from the electronegative sp3 nitrogen atom. Okay, but the dominating mechanism still would be the inductive mechanism, because this nitrogen would not actually tolerate to bear the positive charge on it. Okay, so this would be the dominating mechanism. But compared to the oxygen atom that we have seen in the previous example, nitrogen is less electronegative compared to oxygen. So as a result, compared to the previous molecule in the previous slide, there will be a lesser tendency for the nitrogen to pull the electron density towards it. So compared to the previous molecule, there shall be a lesser magnitude of electron density flow towards nitrogen. Okay, so as a result, the carbonyl carbon will not be as delta positive as the case that we have already observed in the case of the previous molecule. Okay, so which results in a lesser pulling of the sigma bond electron density towards the carbonyl carbon. Okay, and again that results in a lesser stiffening of the pi electron density. Okay, the pi electron density in the carbonyl function group will be stiffened to a lesser degree or lesser extent compared to the case of the molecular system that we have seen in the previous slide. Okay, so as a result, we will have a reduced an increased oscillation frequency for the carbon oxygen functional group, but the oscillation frequency of the carbonyl functional group would still be lesser than the oscillation frequency of the carbonyl functional group in the previous molecule. Okay, so but if we take the case of alkyl substituents on the carbonyl carbon, such as methane, then alkyl groups are notorious electron donators through inductive effect, and as a result, the electron density, say for example, if you consider two CH3 groups, methyl groups attached onto carbonyl carbon, both the CH3 groups will be able to donate the electron density towards the carbonyl carbon. Okay, and which makes the sigma bond a little bit more weakened. Okay, and as a result, since the sigma bond weakens, that reduces the pi bond order as well. Okay, since the pi bond force constant is getting reduced, the frequency of the pi bond also gets reduced. Okay, so the carbon oxygen carbonyl functional group's frequency, stretching frequency, actually gets reduced in this case when we have an electron donor attached to carbonyl carbon. Okay, so then you can compare a ketone with a aldehyde very easily, because for a ketone you have got two alkyl groups attached on carbonyl carbon that can donate the electron density towards the carbonyl functional group. Okay, but in the case of aldehyde, we have got only one alkyl group and one electropositive oxygen. Okay, so as a result, you get electron density donation from only the alkyl group through one alkyl group through inductive effect in the case of aldehyde. So you will not see as much of this effect as you see in the case of a ketone. Okay, so we'll see a little bit higher value for the carbonyl stretching frequency for an aldehyde compared to a ketone. That's exactly what we have seen in the case of aldehydes and ketones in the previous table. If you remember the tabular data that we have shown a couple of slides before. Okay. Again, if we have an alpha halogen attached to the molecular framework in a carbonyl compound, okay, this alpha halogen, next is alpha halogen, which is being connected to an alpha carbon bound to the carbonyl carbon, then the alpha halogen will be able to withdraw the electron density inductively through this the sigma bond of carbon oxygen bond, this typical sigma bond and this typical sigma bond. Okay. As a result, the pi bond order of the carbonyl functional group increases, and which results in a strengthening or increase in the force constant of the carbon oxygen pi bond, which again enhances its stretching frequency. So you will be seeing an increase in the stretching frequency of carbonyl functional groups in this typical case. So that's what exactly you see in the case of acid. Carbonyl functional groups bearing alpha halogens. Okay. Right now, if you have to confirm it's possible, or two configurations possible for the carbonyl compounds such as cis and trans conformers, then what you'll be seeing is a increase in the vibrational frequency of the carbonyl functional group compared for the cis conformer compared to trans conformer. Okay, so here you will have to take into account of the overlap of the 2p orbitals on the vinyl carbons, the carbonyl carbon, and the carbonyl oxygen. Okay, so that means these two carbons, the 2p orbitals on these two carbons, carbonyl carbon and this oxygen. Okay, so if the whole molecule, this whole these three carbons and the oxygen, and if they come in the same plane, the 2p orbitals on these atoms will be able to interact with each other more effectively in a better manner, and that shall form a better delocalization or conjugation of the pi electron density between these two carbons and the carbon and the oxygen here. Okay, so as a result, what happens is, due to the conjugation, the pi electron density on this between these carbons can get transferred onto between these two carbons, which would result in a shifting of the pi electron density between carbon and oxygen towards oxygen, making a negative charge on this oxygen and a positive charge on this carbon. Okay, so which shall reduce the oscillation frequency of this carbonyl oxygen. Okay, and the same thing you can expect here. Okay, the same effect that you can expect here. So you'll be seeing, as a result of conjugation, you'll be anticipating the reduction in the oscillation frequency of the carbon oxygen bond, and basically, if both the molecules are planar, we shall be expecting the same extent of overlap of the 2p orbitals on this 2p orbitals on these four atoms and these four atoms to the same extent, and we shall be then expecting the reduction in the oscillation frequency of the carbonyl functional group to the same extent. Okay, so the key factor here is the overlap of the 2p orbitals on these four carbons and these four carbons, and the plane, if both the molecules are planar, then we shall expect the same extent of delocalization or conjugation that results in same extent of the reduction in the oscillation frequency of the carbonyl functional groups. But actually, in reality, we see a different trend. We see that the carbonyl functional group in here absorbs at a slightly higher frequency than the carbonyl functional group here. Okay, so I'm asking you to find out the reason. So the clues are this: the delocalization of the pi electron density between the vinyl carbons and the carbonyl functional group. Okay, then the planarity. Okay, then you should, if you account for other factors such as maybe it's my clue, steric factor, or maybe structural strain or something like that, then potential energy of the molecule, then you shall be able to reason why the cis conformer absorbs, or the carbonyl functional group in cis conformer absorbs the radiation at a higher frequency compared to the trans conformation. Okay, so I leave this problem up to you. It's very simple to find out the answer. As science students, you are expected to solve this you are expected to find out an answer for this problem on your own. Okay, so it's something like sort of a home exercise for you. Okay, until unless you try to think about these things on your own, you shall you'll not be able to learn anything from this course. Okay, so this course is such a typical course where you have to make a habit of using your brain, your thinking habits, okay, your thought process to find out solutions. Okay, so as an encouragement, as a starting point, I am going to give you this problem, okay, for you to think on yourself. Okay, then the ring strain effect. Okay, here, say for example, the carbonyl function group is a part of, if it is a part of ring, okay, say for example, if you take a cyclic ketone such as cyclohexanone, okay, then we have seen this process before in the case of exocyclic double bonds that are being connected to cyclic ring systems, okay, such as hexane, cyclohexane, cyclopropane, cyclobutane, then cyclopentane, etc. Okay, so say for example, if you take the case of, we are going to use the same approach here, and if you, again, I'm going to give this as an exercise, because we have discussed this before in the case of exocyclic double bonds. And if you consider cyclohexanone, okay, such as the first molecule here, and if you replace the cyclohexane ring with the cyclopentane, then it becomes cyclopentanone. Okay, then if you replace the cyclic ring with the cyclobutane, then it becomes cyclobutanol. Okay, then if you replace the cyclic ring system with the cyclopropane, then it becomes cyclopropanol. Okay, so if you consider this series of starting with the cyclohexanone, then cyclopentanone, cyclobutanone, and cyclopropanol, okay, then you shall be able to see that as you decrease the ring size, okay, that means when you increase the ring strain starting from cyclohexanone all the way up to cyclopropanol, okay, through cyclopentanol and cyclobutanol, okay, you shall be able to see that the carbonyl stretching frequency increases when you go down the cyclic ring size. Okay, so that means cyclohexanone will have the smallest carbonyl stretching frequency, then cyclopentanone will have a slightly higher carbonyl stretching frequency, cyclobutanol will have a little bit more or higher carbonyl stretching frequency, then cyclopropanol will have, of these all molecular systems, cyclopropanol will have the highest carbonyl stretching frequency. Okay, you shall be seeing this trend. Okay, so this has to be attributed to the ring strain, the hybridization of the carbonyl carbon, the p character, 2p orbital character in the hybrid orbitals, and what happens to the 2p character when the ring size decreases. We have already discussed all these factors in the case of exocyclic double bonds on cyclic ring systems. Okay, and a small hint is given on the slide here, and I expect you to find the answer for this question. Okay, and the same thing can be find on esters, cyclic esters such as lactones, where you decrease the ring size. Okay, you shall be see the same effect there, and you shall be see an increase in the carbonyl stretching frequency there. And in the case of amides as well, when you decrease the ring size, cyclic amides such as lactams, when you decrease the ring size, you shall see an increase in the carbonyl stretching frequency. Okay, and for cyclic anhydrates, the same effect can be observed, where when the ring size is reduced, the carbonyl stretching frequency increases. Okay, and if you need further tips, or if you have any confusion, in order to clear the confusion, there are two ways in which you can strengthen the carbon oxygen bond order. One is to remove the sigma bond character. Okay, how do we remove the sigma bond character from the carbon oxygen bond in carbonyl functional group? Okay, attach an electronegative atom such as nitrogen or oxygen onto the carbonyl carbon, so that the electronegative atom withdraw the electron density from the carbon electronegative atom bond, sigma bond, towards the electronegative atom, which makes the carbonyl carbon more delta positive, and which remove the sigma bond character from the carbon oxygen bond. Okay, then the pi bond between the carbonyl carbon and carbon oxygen will become more stiffer. Okay, so that increases the strength of the carbonyl functional group. Okay, bond order of the carbonyl functional group. Or Other way to do is to remove the pi bond character from the carbonyl carbonyl oxygen pi bond. Okay, how do we do it? We bind the carbonyl carbon with a resonance contributor, okay, such as maybe a heteroatom, okay, or an inductive electron donor such as alkyl function groups that would decrease the pi bond character between carbonyl carbon and carbonyl oxygen, okay. So that would in turn will help to increase the sigma bond order between carbonyl carbon and carbonyl oxygen, okay. So these are the two ways in which we increase the oscillation frequency of carbonyl functional group, okay. And other effects that can contribute to the stretching frequency of carbonyl is hydrogen bonding, okay. So how do hydrogen bond affect the carbonyl stretching frequency? Okay, if when a hydrogen bond forms, it happens between an electronegative atom such as oxygen, such as the one in carbonyl functional group, and then between electropositive atoms such as hydrogen, okay, maybe which could maybe a part of a functional group such as OH or NH2, okay. So what happens is when a hydrogen bond is being formed between the carbonyl oxygen and the hydrogen of another functional group, okay, then what happens is the electropositive oxygen atom will polarize the electron density of the carbonyl oxygen more towards it, okay. So oxygen will become slightly infinitesimally small delta positive. That pulls this feature feature of the oxygen pulls the carbonyl oxygen sigma bond electron density towards oxygen, okay, which reduces the sigma bond order of between carbon and oxygen, okay. So that reduces the oscillation frequency of the carbonyl functional group, okay. So there could be different types of pi bond formation. It could be intermolecular not pi bond formation, hydrogen bond formation. It could be intermolecular hydrogen bonding, okay, such as the ones that you see in the case of a dimer of two benzoic acid molecules, or a polymer of two benzoic acid molecules, okay. Or it could be intramolecular. In all these cases, hydrogen bonding reduces the carbonyl functional group's stretching frequency. Already, so having seen that how factors such as inductive effect and resonance effects affect the stretching vibrational frequencies of carbonyl functional groups, then we are going to now consider the stretching vibrations of carbonyl functional groups in several classes of compounds such as aldehydes, ketones, acids, esters, amides, and so on, okay. And we shall be first starting with aldehydes, one of the most popular types of carbonyl compounds which we know about. And basically for aldehydes, except the carbonyl functional group, the rest of the parts of the molecule usually gives higher spectral features that are characteristic or unique to the hydrocarbon framework of the rest of the molecule, okay. And for carbonyl functional groups, the carbonyl functional group usually shows the stretching frequency at 1725 centimeter inverse, and which should be considered only as a base value, and it could be changed upon due to reasons such as hydrogen bonding, resonance contribution, inductive effects, okay. So for example, when the carbonyl functional group is being conjugated with a simple ethylene or vinyl type double bond, okay, then that could reduce the frequency of the carbonyl functional group for reasons that we already discussed, to a value of values between 1680 centimeter inverse and 1700 centimeter inverse, okay. As such, this results in a reduction of the C double bond C stretching frequency to 1640 centimeter inverse, okay. Let's not focus on this one, but rather focus on the carbonyl stretching frequency. Okay, and even when carbonyl functional group is conjugated with a phenyl ring, then you shall expect the reduction in the stretching frequency of carbonyl functional group to in the same range between 1660 centimeter inverse and 1700 centimeter inverse. Okay, then for aldehydes we have the carbon hydrogen carbonyl carbon hydrogen sigma bond. Okay, this sigma bond can undergo stretching vibration, and we shall see the stretching vibration frequency happens something around that 2790 centimeter inverse. Okay, or 2780 or that particular range. Okay, but usually we expect that for the stretching vibration of the carbon hydrogen bond here, we usually expect a single peak or single band in the IR spectrum, but rather we see two bands that are close to each other and resembles something sort of a doublet band structure. Okay, and this happens due to some sort of coupling mechanism where the bending vibration of the carbon hydrogen bond, okay, which happens at something like at 1390 centimeter inverse. Okay, so the frequency of this bending vibration, which is the fundamental frequency, and when you multiply the frequency of this bending vibration 2 into with the 2 or with a factor of 2. Okay, so 2 into 1390 centimeter inverse comes around at 2780 centimeter inverse. Okay, so that means essentially the double the fundamental frequency of bending vibration is called this first overtone. Okay, the first overtone of the bending vibration happens at 2780 centimeter inverse. Okay, that's exactly where the stretching vibration of the fundamental frequency of the stretching vibration of carbon hydrogen bond lies. Okay, so that means the fundamental stretching vibration of the carbon hydrogen bond can couple with the first overtone of the bending vibration of the carbon hydrogen bond. Okay, so we call this interaction between a fundamental frequency of a typical vibration with the first overtone of the another typical vibration as a Fermi interaction, and due to this Fermi interaction, the stretching vibrational frequency of the carbon hydrogen bond will be split into two types of vibration, one with a higher energy or higher frequency, and the other vibration with a lower frequency. Okay, so as such we shall see two bands corresponding to these two sets of vibrations, one at frequency at 2820 centimeter inverse and the other one at frequency of 2720 centimeter inverse. Okay, and this pair of bands or doublet structure is called a Fermi doublet. Okay, but usually it can be seen for some aldehydes, but usually for aldehydes which contains sp3 CH bonds, the sp3 is the vibrational band, stretching vibrational band for sp3 CH usually comes around in the region of 2800 centimeter inverse. Okay, and it's a strong band, and this vibrational frequency of the or vibrational band of sp3 CH may sometimes hide or obscure the bending stretching vibrational band of the carbon hydrogen bond here. Okay, this spectrum shows the IR spectrum of this typical aldehydic molecule where we have cyclohexyl carboxylaldehyde, and the peaks we should focus on right now is the peak that appears at around 1720 centimeter inverse, which is a strong peak because, and this is due to the carbonyl functional group stretching frequency, and it's a strong peak due to the fact that carbon and oxygen are they differ in electronegativity. Okay, so and there is a typical dipole moment that exists in the carbonyl functional group, which changes significantly when the carbonyl oxygen or carbonyl functional group vibrates. Okay, and then this part of the band, okay, the band at around say 2700 centimeter inverse is usually due to the stretching vibration of the carbon hydrogen bond. Okay, but we shall expect a Fermi doublet here. We do have a Fermi doublet structure here. The only thing is that the higher frequency band of the Fermi structure actually overlaps with the sp3ch vibrational frequencies or vibrational bands of the cyclohexane system here. Okay, so we don't, the band is there, the band of the Fermi structure is there, but it overlaps with the sp3ch vibrational bands. Okay, and the rest of the lower frequency region of the spectrum actually are due to the cyclohexane ring structure here. And this one is a spectrum of benzaldehyde, and from the spectrum it is apparent that the band of carbonyl functional groups comes around 1700 centimeter inverse. Okay, but if you consider the carbonyl band which is being connected to cyclohexane ring size, okay, it was at around 1720 centimeter inverse. But here the band is at a slightly lower frequency, okay, by a factor of 20 centimeter inverse. That is because of the conjugation effect of the carbonyl functional group when it is being conjugated with the phenyl ring here. Conjugation reduces the bond order of the carbonyl functional group here and reduces stretching frequency by a factor of 20 centimeter inverse. Okay, and then the rest of the parts of the spectra are self-explanatory. You can deduce that this band, this doublet structure is due to the stretching vibration of the CH functional group here, and this is the Fermi doublet, which results as because of the coupling between the CH stretching vibration with the first overtone of its bending vibration. Okay, and that can be really discerned because there are no sp3ch here, rather we have sp2ch, which absorbs slightly towards the higher frequency end of the spectrum. That means about 3000 centimeter inverse, which makes it further away from the Fermi doublet. Okay, and as for the phenyl functional group, you can see the asymmetric stretching vibrations of the aromatic carbonyl C-double-bond-C bonds of the phenyl ring between a region of 1400 centimeter inverse and 1600 centimeter inverse. So these are signature print bands for the phenyl ring system here. Okay, but whereas for cyclohexane ring system that we have seen in the previous spectrum, we didn't see such kind of bands. Okay, and this is a monosubstituted phenyl ring, and if you remember the case of the cases where we discussed for monosubstituted or substituted mononuclear ring systems, okay, then you can see that the out of plane bending vibration of the aldehyde functional group above and below the plane of the phenyl ring usually happens between a range of 700 and 800 centimeter inverse. Okay, so these bands are signature bands for monosubstituted phenyl ring system. Okay, and for ketones, the spectrum is much simpler compared to aldehydes because you don't have any CH stretching vibration or CH bending vibration in the case of cetones. Okay, the CH bond, in the sense the CH bond of the carbonyl carbon and the hydrogen that is being attached to it in the case of aldehydes, which lacks in the case of ketones. Okay, we do have simple carbonyl functional group here, which oscillates at a frequency of 17-15 centimeter inverse when it undergoes stretching vibration, which is a lower frequency compared to the case of carbonyl functional groups in aldehydes. Okay, that again due to the inductive effect of the alkyl groups attached to the carbon in the case of ketones here. Okay, and this again should be taken, this value should be taken as a base value only, because it can shift according to the nature of the substituents on the carbonyl carbon. Okay, so when there is conjugation when the conjugation is extended for the carbonyl functional group, the frequency reduces to a range between 1675 centimeter inverse and 1700 centimeter inverse, and it's the same frequency range for carbonyl functional groups in conjugation with the phenyl ring. Okay, and for carbonyls attached to cyclic ring systems such as cyclohexane or cyclopentane, the frequency of the carbonyl functional groups comes between 1705 to 1815 centimeter inverse, and this frequency increases as when the ring size decreases. Okay, and we have already discussed about this typical trend. Okay, and the reasons of of this effect. Okay, then the bending vibration of this typical. For ketone, the carbonyl carbon should be attached to two other carbons of a typical alkane system or typical cyclic ring system such as cyclohexane. So this bond can undergo bending vibration, and this bending vibration can happen between a range of 1100 and 1300 centimeter inverse. So these are the typical vibrational frequencies that you can expect in the case of the IR spectra of ketones. Okay, so this spectrum shows the IR the features of the IR vibrational bands of a simple ketone such as 3-methyl-2-pentanone. Okay, so what you'll be expecting is just the stretching vibration of the carbonyl carbon here, which usually comes around 1710 centimeter inverse, and rest of the part is dominated by the hydrocarbon framework of the molecule, such as sp3ch bands here. Then this part of the bands are due to the carbon-carbon vibrations and the vibrations between the carbon-carbon bonds between the carbonyl carbon and the sp3 carbons here. Okay, so this spectrum shows the IR spectra of a carbonyl carbon which is bound to a C double bond C, a vinyl type bond here. Okay, and as you know, for such a system we can have the carbonyl stretching frequency that is being observed at around 1700 centimeter inverse, and this reduction in the frequency of the carbonyl functional group is due to the conjugation between the carbonyl functional group and the vinyl double bond here. Okay, and then you shall see the stretching frequency of the C double bond C of this vinyl type bond here, and which is actually being conjugation with the carbonyl functional group at around 1600 centimeter inverse. So you should compare this peak with the case of vinyl C double bond C stretching. Okay, just go back a few seconds before and see the spectra of aldehyde that is being bound to the phenyl system. Okay, I'm talking about the benzaldehyde system. Okay, so compared to that case here, you just have only one peak for the C double bond C stretching here. Okay, and then you see the classic bands of sp3ch stretching vibrations of the sp3 carbons here, carbon hydrogen bonds here, then sp2ch vibrations of the this typical CH here. Then you see an overtone, first overtone of the CS stretching vibration here. Okay, CS stretching vibration happens at 1700 centimeter inverse, and the first overtone happens at around 2 times of this frequency, which is 3400 centimeter inverse. Okay, then this one is a typical C double bond C system. Okay, where the carbons are tri-substituted. Okay, this carbon bears a typical functional group, this one, and this carbon bears another functional group, and this carbon bears another functional group. Okay, so it's a typical tri-substituted vinylene system. And so for such a vinylene system, as if you remember, the out of plane bending vibration of the functional group comes around 820 centimeter inverse. That's exactly what you see here. Okay, so this one is a discernible signature band of the tri-substituted vinylene type system, as we have seen in this typical case of molecules. Okay, as we see in this typical molecule. Okay, in the case of a molecular system such as a ketone, where the carbonyl functional group is being bound to a phenyl ring, what you would be expecting is a conjugation or delocalization of the phenyl ring pi electron density with the carbonyl pi electron density here, which reduces the pi bond order of the carbonyl functional group, which again reduces the carbonyl stretching frequency to a value of 1690 centimeter inverse. Okay, something around 1680 centimeter inverse. Okay, and then what you'll be expecting is the asymmetric stretching vibrational frequencies or bands of aromatic C double bond C bonds here, then the CS stretching vibrations of sp3 hybridized carbon methyl carbon hydrogen bonds here, then above that you shall be seeing sp2ch stretching vibrations somewhat here of the phenyl carbon hydrogen bonds here. Then you shall be expecting a bending vibrational frequency of the C or C system here at around 1300 centimeter inverse. Okay, and this then you shall be seeing the typical band structure of the monosubstituted out of plane bending vibration of the this typical functional group of the phenyl ring system connected to the phenyl ring system here. Okay, so this one is a monosubstituted phenyl ring where the functional group can undergo out of plane bending vibration, and this vibration comes at around in this typical region between 1650 centimeter inverse and 800 centimeter inverse. Okay, so in some cases of ketones, you could expect keto-enol tautomerism, okay, where you have a carbonyl functional group, and then to this you have a alpha carbonyl functional group. Okay, so in this typical case, when the molecule, if the molecule can adopt such a structure, okay, and then the molecule can undergo keto-enol tautomerism. The classic keto-enol tautomerism. You have been learning this one from the undergraduate classes. Okay, so as a result of keto-enol tautomerism, what happens is one of the carbonyl oxygen occurs an OH character. Okay, it will be can be treated as a OH functional group, and this typical carbon-carbon bond becomes a double bond. Okay, and this carbonyl oxygen and the OH here may form an intramolecular hydrogen bonding. Okay, so as a result, what happens is you shall expect the carbonyl stretching frequency of the ketone or carbonyl functional groups in the ketone structure here. This is a keto structure. The carbonyl stretching vibrational frequency of keto structure. Okay, then you shall expect the carbonyl stretching vibrational frequency of the enol structure here. This one is the enol structure. And then you shall also expect the OH stretching vibrational frequency of the enol. Okay, so unlike a classic ketone, you shall expect the vibrational stretching vibrations of the carbonyl functional groups of both keto form and the enol form. Okay, then the OH stretching vibration as well. Okay, in addition to the hydrocarbon framework or bond vibrations of the molecular systems here. Okay, so for the keto tautomer, the carbonyl vibrational frequency for this typical molecule appears to be as a doublet structure, because the carbonyl functional groups shares a common group CS2 group here, or the carbonyl carbons are connected by a common carbon atom. Okay, so and this part of the molecule is identical to this part of the molecule. Okay, they are being connected by, since they are being connected by a common atom here, this common atom can couple the vibrational frequencies of these two carbonyl functional groups. Okay, so in effect we have a mechanical coupling between the vibrational frequencies of the carbonyl functional groups, and this mechanical coupling splits the vibrational frequencies of the carbonyl functional groups, which otherwise would have been occurring at the same frequency, but this coupling splits that frequency into two different frequencies, one at a higher frequency and the other one at a lower frequency with respect to the vibrational frequency of an isolated carbonyl functional group. Okay, so the higher frequency happens at around 1723 centimeter inverse, and the lower frequency vibration happens at around 1706 centimeter inverse. Okay, as for the enol tautomer, you shall see the carbonyl stretching frequency at a slightly lower frequency compared to the carbonyl stretching frequency of the keto form, and this is basically due to an effect nothing but the hydrogen bonding, intramolecular hydrogen bonding between the carbonyl oxygen and the OH functional group here. Okay, and then you shall see the OH stretching frequency between a range of 2400 centimeter inverse to 3200 centimeter inverse right here. Okay, and the rest of the part, see, this is the spectrum, the doublet structure of the due to the stretching vibration of the carbonyl functional groups in the keto tautomer, then the stretching vibration of the carbonyl functional group in the enol tautomer, then the OH stretching vibration due to the OH in the enol tautomer, then the remaining part of the spectrum due to the hydrocarbon framework of the molecule. Okay, and you shall see the band at around 1400 centimeter and 1500 centimeter inverse due to the stretching vibration of the C double bond C bond in the enol tautomer. Okay, and you shall see bands due to sp3ch bonds that comes around 2800 centimeter inverse right here. Okay, which are weak bands in here. Then sp2 hybridized ch, which comes around 3000 centimeter inverse here, which overlaps with the OH stretching frequency. Already, right now we jump onto the case of esters, and unlike aldehydes and ketones, esters do have an sp3 hybridized oxygen bound to the carbonyl-carbon through a sigma bond. And for reasons that we have enumerated before, where we discussed the competitive mechanisms of inductive and resonance effects, you shall be able to see that the oxygen bound to the carbonyl-carbon, the sp3 oxygen bound to the carbonyl-carbon, enhances the carbonyl vibrational frequency compared to the case of aldehydes and ketones. And this enhancement results in the carbonyl vibrational frequency of esters to lie at a frequency somewhere around 1735 centimeter inverse, and this should only be taken as a base value, and it can be changed upon conjugation. For example, when we have the carbonyl functional group conjugated to C double bond C, or such as the one in vinyl functional group, and such as a phenyl functional group, then the vibrational frequency could fall into a region of 1750 to 1735 centimeter inverse. And due to, if you have an extra sp3 hybridized oxygen that is bound to the carbonyl-carbon, then that results in an increase in the vibrational frequency to a further higher value, such as the ones between 1760 and 1765 centimeter inverse. And as for cyclic esters such as lactones, here the vibrational frequency of carbonyl functional group comes between a range of 1740 to 1850 centimeter inverse, and this vibrational frequency can further be enhanced by a reduction in the ring size. Okay, the ring size of the cyclic ring system here. Okay, and the stretching vibrational frequency of the carbonyl-carbon and the sp3 hybridized oxygen usually falls in a range of 1000 to 1300 centimeter inverse. And this one is a typical spectrum of a simple ester such as ethyl piviolate, and you can see the carbonyl stretching frequency as a strong band, single strong band at around 1720 centimeter, 35 centimeter inverse, and 1735 centimeter inverse. Then the carbon oxygen vibration, which usually appears to be around between 1100 and 1200 centimeter inverse. Okay, so this typical band is what I'm talking about: carbon oxygen stretching vibration and the carbonyl stretching vibration. Okay, and the rest of the again spectrum is being dominated by the hydrocarbon part of the molecule. Okay, and moving from esters to the carbonyl functional groups in carboxylic acids. Okay, carboxylic acids is typical functional groups where we have a carbonyl functional group and then an OH functional group, where the sp3 OH of sp3 oxygen of the OH functional group is bound to the carbonyl-carbon through a sigma bond. Okay, so this effect of alternative oxygen bound to the carbonyl-carbon of the carbonyl functional group reduces the carbon oxygen vibrational frequency to around 1710 centimeter inverse. Okay, so the carbon oxygen stretching frequency can be found around this typical value, and again this should be taken as a base value because it can be reduced by means of conjugation effects when the carbonyl functional group is bound to a C double bond C, such as the one in vinyl system, or a C-dog bonds in a phenyl aromatic system such as phenyl ring. Okay, then the stretching vibration of carbon oxygen bond, carbon of the carbonyl function group, and the oxygen, sp3 oxygen of the OH functional group. Okay, so this stretching vibration usually appears between a range of 12-10 centimeter inverse and 13-20 centimeter inverse. Then the stretching vibration of OH functional group, OH bond, comes between a range of 2400 to 3400 centimeter inverse. Okay, so you shall expect a sharp peak corresponding to this one, then another peak corresponding to this one, then a very broad peak corresponding to the OH stretching vibration of the carboxylic acid functional group. And this one is a typical spectra of a carboxylic acid, organic carboxylic acid, where you see the carbonyl vibrational frequency has a strong band at around 17-10 centimeter inverse. Then you shall see the OH stretching vibration as a very broad band, that very broad structureless band, I would say structureless band, between 2300 centimeter inverse and which spans all the way up to 3500 centimeter inverse. It's a very broad band, okay, which you cannot actually see in the case of other functional groups. Okay, so it's very easy to distinguish or discern an OH functional group that is being bound to a carbon, such as the one in case of a carboxylic acid. Okay, then you shall see the carbon oxygen stretching vibration as a set of bands between 1100 and 1400 centimeter inverse. Okay, it's pretty easy to interpret these bands. Okay, and the carbon double bond structure bands usually comes between 1300 to 1600 centimeter inverse, and both the sp3ch bands and the sp2ch bands are deeply buried in the OH band system here. Okay, so this one is a IR spectrum of a typical carboxylic acid, and you can see that the CO stretching vibration comes around 1710 centimeter inverse or 1700 centimeter inverse here, and there is no conjugation effects here. Then the OH stretching vibration spanning all the way from 2400 to 3500 centimeter inverse, and the sp3ch band vibrations of the methyl groups somewhere around here. Okay, then the CS stretching vibration at around 1200 to 1300 centimeter inverse. Then this band structure is due to the out of plane bending vibration of the OH functional group with respect to the plane of the rest of the molecule. Okay, so this one is a spectra of the carboxylic acid rings functional group, where the carbonyl functional group is being bound to a phenyl ring system here, so that there could be effective conjugation between the carbonyl pi bond with the pi bond structure of the phenyl system here. Okay, and which reduces the carbonyl stretching frequencies to a low value, and that appears to be at around 1680 centimeter inverse. Then you shall see the carbon double bond stretching frequency of the phenyl ring somewhere here. Then the OH stretching vibration frequency, which ranges between 2400 centimeter inverse all the way up to 3300 centimeter inverse, but rather appears as a little bit more structure in the case of aromatic carboxylic acids. Then we see the sp2ch, which is buried between the band structure of the OH band here. Then we see the OH out of plane bending vibration of the OH functional group above the plane of the phenyl ring at around 1900 centimeter inverse. And by the way, this one is a monosubstituted phenyl ring system here. So this band is typical of the monosubstituted phenyl ring system here. And as for acid anhydrides, we usually have two carbonyl functional groups which are being bound to, or which are being connected by a common atom in between, oxygen in between. So we expect these carbonyl functional groups to interact with each other through mechanical coupling, which usually results in the splitting of the carbonyl functional carbonyl stretching frequency, and we see these bands between 1800 to 1830 centimeter inverse. And once we have conjugation of the carbonyl functional group with the C-Dowbones or aromatic ring system, the band structure, the frequency of the carbonyl functional group reduces to a value between 1740 and 1778 centimeter inverse. Okay, and for the CO band here, we see the stretching vibration between 900 and 1300 centimeter inverse. We see a multiple of bands here. So this one is propionic anhydride, and the IR spectrum shows the carbonyl stretching frequency as a system of doublet bands, which is due to mechanical coupling of both these carbonyl function groups through the intermittent or intermediate oxygen atom. Okay, then you shall see the carbon oxygen band at around 1000, carbon oxygen stretching band at around 1000, well above 1000 centimeter inverse, and then sp3ch bands just about 2800 centimeter inverse. Okay, for acid halides, where the carbonyl carbon is bound to a chlorine, a halogen atom such as a chlorine atom, the carbon oxygen vibrational frequency, carbonyl vibrational frequency appears at a frequency range of 1775 to 1810. Okay, at a higher frequency compared to aldehydes and ketones. That's obviously due to the inductive effect of the chlorine atom. Okay, and so when this carbonyl is being conjugated to a phenyl system such as a phenyl ring, we see additional bands. Okay, and we see a reduction in the frequency of the carbonyl vibration. Then the carbon, if the halogen is chlorine, the carbon chlorine vibration usually comes between a range of 550 to 730 centimeter inverse. When it is bromine, the vibration is usually seen in this typical range, and when it is iodine, vibration frequency is further reduced. Okay, but usually if you see the IR spectrum range, we usually detect only the band corresponding to the carbon chlorine bond. We don't normally see the bands because this is beyond the detection limit of the IR spectrophotometer normally. Okay, for propionyl chloride, where we have a chlorine bound to carbonyl carbon, we see the carbon chlorine vibration at around just about 900 centimeter inverse as a a V-shaped or rather a U-shaped band, a strong band. This is a strong band because of the inherent dipole moment in the carbon chlorine sigma bond, because chlorine is highly electronegative compared to carbon. So you should be able to expect, or you shall expect, a significant change in magnitude of the dipole moment when this typical bond vibrates. Okay, and the carbon oxygen vibrational frequency, carbonyl vibrational frequency appears to be around 1790 centimeter inverse. For amides, the carbonyl carbon is connected to a nitrogen atom, which is a little bit more electronegative compared to carbon. Okay, carbonyl carbon. So you shall expect, and this nitrogen normally bears a lone pair electron density. So you shall expect a competition between resonance effect and inductive effect there. And as we have seen before, the inductive effect normally wins over the resonance effect, making the carbon oxygen bond, pi bond, more stronger, which results in a higher frequency at around 1685 centimeter inverse. So the NH stretching frequency of the amide system here, that usually appears to be at around 3300 centimeter inverse, and this higher frequency is due to the lighter atom hydrogen here. Okay, and because when we have lighter atoms such as hydrogen in the bond structure here, we typically have a low reduced mass, which results in a higher stretching frequency. So when this amide system is a part of the cyclic ring structure such as lactams, we see that the carbonyl vibrational frequency increases with a reduction in the size of the ring. Okay, so as the ring size decreases, the carbonyl vibrational frequency increases, and the bending vibration of the NH bond usually occurs between 1550 centimeter inverse and 1640 centimeter inverse. Okay, and this NH bond can undergo out of plane bending vibration when the amide system is a part of a ring structure, okay, or even being connected to a cyclic ring. Okay, so this usually occurs between 800 centimeter at around 800 centimeter inverse. So this one is a typical spectrum, IR spectrum of an amide such as pi-wall amide. Okay, where you can see the CS stretching vibration has a strong band structure at around 1700 centimeter inverse. Then this is a typical primary amine, so you shall see a W-shaped peak of medium to strong intensity, okay, between 3100 centimeter inverse and 3600 centimeter inverse. Okay, so this is a typical aspect of a amide. Okay, now having finished the carbonyl compounds, we move on to two other types of compounds. First one is nitro compounds, and it's one of the most frequently encountered type of functional group in organic molecules, such as nitrobenzene, which is one of the simplest molecular system we know, which contains nitro group, functional group. Okay, so and as you know, the nitro group can have this typical intermediate resonance structure, where one of the both the nitrogen and oxygen bonds have partial double bond character, bearing or having the pi electron density shared between these two nitrogen and oxygen bonds, whereas the nitrogen atom has got a positive character. Okay, so as a result, and the vibration frequency, nitrogen oxygen vibration frequency, usually comes between a range of 1530 to 1600 centimeter inverse, where you can see two bands. One for symmetric stretching and one for asymmetric stretching. Okay, so the symmetric stretching vibration for aliphatic nitro compounds usually comes between 1300 to 1390 centimeter inverse, whereas asymmetric stretching vibration usually comes between a range of 1530 to 1600 centimeter inverse. Okay, for aromatic nitro compounds, the symmetric stretching vibration of the nitro compounds, nitro functional group, comes between 1350 to 1355 centimeter inverse, and for asymmetric stretching, it comes between 1490 to 1550 centimeter inverse. So you can see both the symmetric and asymmetric stretching vibration frequencies for aromatic nitro compounds is lesser than that of aliphatic nitrogen compounds, and if you think about it, you can find the answer very easily why is it happens so. Okay, and this one is a IR spectra of nitro compounds such as 2-nitropropane, and just like that we have discussed before, the symmetric stretching vibration of the nitro group here, both these two bonds here, NO bonds here, usually happens between 1300 to 1400 centimeter inverse. Okay, and the asymmetric stretching vibration, okay, where one bond compresses and the other one stretches out, happens between a range of 1500 to 1600 centimeter inverse. So these are the major dominant band systems of nitro compounds here. Okay, and the rest of the bands are being contributed by the hydrocarbon part of the molecule. Okay, and the other type of functional group we discuss about nitriles. Okay, C triple bonded. Okay, so for nitriles, the C triple bond and vibration usually happens at around 2250 centimeter inverse. Okay, this is due to I'm talking about the symmetric stretching vibration, and this again depends upon conjugation, because the double bond pi bonds in here between carbon and nitrogen can take part in conjugation with other pi bond systems. Okay, and this vibration frequency usually falls in this region because the reduced mass of carbon and nitrogen are not much different, and though there is a slight difference between electronegativities of carbon and nitrogen. Okay, and because of the difference in electronegativity between carbon and nitrogen, the carbon nitrogen bond between in the nitrile system is slightly more polarized rather than between carbon triple bonds. Okay, and this change polarized triple bond, actually when it vibrates, the dipole moment changes to a significant magnitude, making the band of a significant intensity. Okay, so this one is a typical intense strong band, which is actually very narrow for the stretching vibration of a terminal nitrile functional group in propionitrile. Okay, so you can see other than this band, the rest of the bands are due to the hydrocarbon part of the molecule. So we are almost coming to the end of IR spectroscopy, and you don't have to remember all these band structures and all the values, but you should at least remember some minimum things. Okay, so the first thing we have talked about before, you need to notice the shape of the bands, whether it's a broadened, really broadened band. Okay, if it is a really broadened band which comes around above 3000 centimeter inverse, usually due to OH and alcohol functional group or carboxylic acid. And if it is a W-shaped band about 3000 centimeter inverse, that is due to a primary amine. Then if it is a V-shaped band at the same region, that is due to a secondary amine. And if it is a something like a very sharp spikes, that is due to CH of a sp hybridized carbon. Okay, carbon hydrogen bond. Okay, and if it comes out as a shoulder to a band system, then that is due to CH of a sp2 hybridized carbon. Okay, so we have already talked about the shapes. Okay, then right now coming to the values, you need to see the trend of the values. Okay, you need to at least remember these values and see, you need to have logic of where to find these values. Okay, so we start with the functional groups that shows the vibrations at a higher frequency, such as OH. Okay, OH shows vibrational frequency above 3000 centimeter inverse, or sometimes starts from 2500 centimeter inverse and goes all the way up to 3600 centimeter inverse. And NH, such as the one in primary amine or secondary amine, shows bands at a 3400 centimeter inverse. OH is a very broadened band, whereas for NH in primary amine is a W-shaped band, NH in secondary amine is a V-shaped band, or rather a U-shaped band. Then the carbon hydrogen vibrations usually comes around 3000 centimeter inverse. So we start with the CHO here, carbon hydrogen vibration CHO aldehyde, that is usually being seen at as a doublet due to Fermi resonance, one at 2850 and the other one at 2750. Then when we come to sp3ch, we see bands between 2800 and 2900 centimeter inverse. Okay, just below 3000 centimeter inverse. Above 3000 centimeter inverse, the CH vibrations are primarily due to sp2ch and sp3ch. sp2ch vibrations are seen at around 3100 centimeter inverse, and SPCH vibrations are seen at around 3300 centimeter inverse. Okay, if you remember correctly, the sp3ch vibrations are a set of high intensity bands. sp2ch vibrations are again a set of high intensity set of bands, but not as much intense as the SPCH bands. Okay, and the SPCH bands are really it's not actually a set of bands, it's actually a very sharp spike type band at around 3300 centimeter inverse. So it's easy to distinguish these band systems. Then again, for CH bands, for methyl and methylene functional groups, the CH bending vibration usually happens at around 1465 and 1365 centimeter inverse respectively for CH2 and CH3. Then nitrile systems, C triple bond N comes at around 2250 centimeter inverse. That's pretty easy to identify because there is not much difference in the reduced mass of carbon and nitrogen, so therefore it comes close to the frequency range of C triple bond C. Okay, which comes at around 2150 centimeter inverse. Then carbonyl is typically around 1750 centimeter inverse. Okay, and we shall start with the lowest frequency one, the amides. Okay, the amide shows carbonyl at around 1690 centimeter inverse. Acids show at 1710 centimeter inverse. For reasons we know, ketone shows at 1715 centimeters inverse. So if you take ketone as a benchmark, above ketone we have got acids and amides. Below ketone we have aldehyde, which shows frequency at around 1725 centimeter inverse. For ester, carbonyl frequency comes at around 1735 centimeter inverse. For acid chloride, the frequency is at around 1800 centimeter inverse. And anhydrides, okay, which shows two peaks due to mechanical coupling of the two carbonyl functional groups. Okay. Then C double bond C. Okay, you can expect this one in aromatic ring systems as well as sp2 carbon-carbon double bond systems in non-aromatic ring systems. Okay, so for the major difference between them is that for aromatic ring systems such as benzene, the C double bond C vibrations shows up as a set of bands between 1400 and 1600 centimeter inverse. Okay, but for systems other than aromatic ring systems, C double bond C usually appears, say for example, for vinyl system, appears as a single sharp peak between 1400 and 1600 centimeter inverse. Okay, then carbon oxygen bond vibration usually shows up at around 1100 centimeter inverse. Okay. Then again, carbon halogen, for example, carbon chlorine bond vibration usually comes at as an intense peak, very intense peak at around between 900 and 1000 centimeter inverse. Okay, so how do we, when we get an IR spectrum, how are we going to find out the peaks and interpret the spectrum? So that is a question. Okay, so if you need to find out the molecular structure from a given IR spectrum, you should start to look for peaks. Okay, but you can develop a protocol to look for the peaks, or a methodology, or an a typical format. Okay, to look how, or to look out for how to find out the peaks and how to assign the peaks to a typical bond or a typical functional group. Okay, so a good rule of thumb is that for me personally, I start looking for OH first, whether the molecule has got an OH. It's very easy to distinguish the OH functional group band from other bands. Okay, because OH band is really broad. Okay, so if you have a OH band, then obviously it's either an alcohol or a carboxylic acid. Okay, so then if there is an OH, then I look for carbonyl band. Okay, C double bond. Okay, so when we look at the carbonyl band, if you see that there is a band at around, sharp band at around 1700 centimeter inverse, or somewhere around 1700 centimeter inverse, then if there is a band, such a band, then see whether the band is split into two, such as a doublet structure. Okay, if there is a doublet structure, it's most probably an anhydride which contains two carbonyl functional groups. Okay, so if there are not two bands, but instead we have only one band, okay, then there is one carbonyl functional group, then what you do is confirm that there is the OH, okay, which we have already looked in the spectrum already in the beginning. Okay, so if there is a band for OH as well, then we have band for CO, carbonyl functional group, and OH. Okay, then we have an carboxylic acid. So, but if the band is absent, OH band is absent, then look for in the same region, okay, around 3400 centimeter inverse or 3300 centimeter inverse, look for the bands of NH. Okay, NH2 or NH. Okay, for NH2 we see a W-shaped band at 3300 centimeter inverse. For NH we see a sharp V-shaped band at the same range. Okay, so if there is such a band, NH2 or NH is most probably a combination of carbonyl and NH. Okay, that or NH2, that makes it an amide. Okay, it could be an amide most probably. Okay, then if there is no such band, look for CO band between 1000 and 1200 centimeter inverse. Okay, so if such a band is there, it could be carbonyl and CO, makes it an ester functional group. Okay, if there is no such a band, then look for the CH band. Okay, CH band, that means the CH vibration at around 2700 90 centimeter inverse, okay, but which appears as a doublet due to Fermi resonance of the bending vibration of the carbon hydrogen bond of the CHO functional group. Okay, so if there is a doublet at around 2000, something like a 2750 and 2820 centimeter inverse, then it could be a aldehyde functional group. So if none of these bands are present, then we have only carbonyl functional group. It could be a ketone. Okay, so but when we look for the carbonyl functional group, if there are no peaks for carbonyl functional group, then look for other functional groups. Okay, look for the band of OH. If there is an OH functional group, but if CO is absent, then it's an alcohol. Okay, so the same protocol we follow here. If there is no OH and no CO, look for NH. Okay, if you see a W-shaped band at 3300 centimeter inverse, it could be a primary amine. If you see a rather sharp V-shaped band in the same region, it could be a secondary amine. Okay, if none of these are present, look for CO bands at around 1000 to 1200 centimeter inverse. Then if it's just a CO band without carbon, it could be an ether. Okay, if this is not present, look for C triple bonded. Okay, CN at around 2200 centimeter inverse. Okay, a sharp band, a very sharp band. Then it could be nitrile. Okay, and if that is absent, look for C triple bond C. Okay, a little bit lighter, smaller frequency compared to C triple bond. Then it could be an alkyne. Okay, if this is not present, look for C double bond C vibrations between a range of 1400 and 1600 centimeter inverse. Okay, if there are multiple peaks, it could be benzene or aromatic ring system. If there is just one peak, it could be an alkene. Okay, if none of these bands are present, look for NO2 vibration. Okay, look for two vibrations. The symmetric switching vibration at around, the sharp peak at around 1300 centimeter inverse, and another vibration. Okay, at around 1400, between 1400 and 1500 centimeter inverse. Okay, which is the asymmetric switching vibration. If two such bands are present, that could be nitro compound. Okay, if none of these are present, look for a sharp intense peak at around 1000 or between 900 and 1000 centimeter inverse. It could be due to the carbon chlorine bond vibration. So it could be halide. So that's it. We have finished the topics on IR spectroscopy. Shortly, I will give you an assignment on the IR spectroscopy, and I will submit. I will upload the assignment in our classroom, and you need to submit the responses within maybe 1 or 2 weeks. And in the next class, we will start discussing NMR spectroscopy. Okay, thank you.